So for problem number 11, it says that there's a baseball on the moon and an identical baseball on Earth, and are thrown vertically upward in the same initial velocity of 13 meters per second. What's the difference in the maximum height the ball reaches on the moon compared to the Earth? The acceleration due to gravity on the moon is 1/6 that of Earth. So what's the first thing we do for a physics problem? We're going to have to draw a picture. So this is the Earth, perfectly drawn Earth. There's the land. That's the North and South Pole. It's ice. Get it? All right. So anyways, there's a ball that's thrown up in the air. But also on the moon over here, which is much smaller than the Earth, that same baseball is thrown up in the air. Now, the baseball is not relative or not proportional to the, that's a really big baseball if you compare that to the size of Earth. But we throw them straight up in the air. And this one has a velocity in the y direction. So we'll say v sub y 0 is equal to 13 meters per second. And then this one has the same thing over here. V sub y 0 equals 13 meters per second. Okay? And so we got to figure out what's the maximum height. Now the maximum height, when it gets to the maximum height, so this is an interesting one. We're going to need a kinematic equation to do this. So at the maximum height on Earth, well, it's the same on both of these. Vy at the max is 0, right? Because when that ball gets way up here, just in that instance before it changes direction and goes back down, at the maximum height, for that instant in time, it's going to be 0 seconds. We also know that the acceleration due to gravity is going to be negative 9.8 meters per second. And so there's a formula that we could use, and I'm going to switch it up a little bit. That says v sub y is equal to v sub y initial squared plus 2 times the acceleration. Oops. Well, it is technically g, but we'll 2 times the acceleration in the y direction times, and we'll call this delta y. And delta y is going to give me my maximum height. Remember that delta y is equal to my y final minus my y initial, and way down here, my y initial is 0 meters. So the maximum height is just basically going to be y, right? Because when I say minus 0, I'm just going to be left with y. So anyways, I need to plug some numbers in and figure out what I get. So for Earth, it's going to be my v final. This is 0. So I get 0 squared, which is actually 0. This is going to be 13 squared plus 2 times negative 9.8 meters per second times delta y, which is what I'm solving for. Okay? All right. So I end up with 13 squared is going to be 169, I think. Let's double check on our calculator. Yep. So this becomes 0. I'm going to start up here. This becomes 0 equals 169 minus 16.9, I think. Let me do it on the calculator. Yep. Or 19.6. I said it backwards. $19.6 times delta y. So I subtract 169 from both sides. This is basic algebra. I get negative 169 is equal to negative 19.6 times delta y. Divide both sides by negative 19.6. And then I get the maximum height of Earth is, well, let me do the math before I get too far ahead of myself. 169 divided by 19.6. It's about 8.62 meters. So we'll do 8.62 meters. So right up here is about 8.62 meters. Okay. Now we do the exact same thing for the moon, except our acceleration due to gravity is actually negative 9.8 meters per second squared. It's 1/6 of Earth, so I've got to divide that by 6. So I'm going to say, which if I remember right, it's like 1.63. 9.8 divided by 6. Yeah, 1.63. So this is a negative 1.63 meters per second squared. So we do the exact same thing. We're going to say y sub v sub y squared is equal to v sub y naught plus 2 times the acceleration times delta y. Plug that in. This is still 0, right? Because when this ball goes up, my final velocity in the y direction equals 0 meters per second. Okay, so that's squared. This initial velocity is still 13 meters per second squared, minus 2 times 1 point, or well, plus 2 minus 1.63 delta y. So I'm going to skip a step here. Over here, I'm going to have a negative 169, and then over here, I just got to multiply this times 2. And so it's a negative 3.27. So it's a negative 3.27 times delta y. Divide both sides by negative 3.27. Need my calculator. So 169 divided by 3.27. It's about 51.7. So if you throw that same ball, that same baseball at the same velocity on the moon, it actually goes 51.7. But the question is, what's the difference? By the way, what do you think? What do you think this 8.62 is when I multiply it by 6? 8.62 times 6. Now we did some rounding. So one thing, this isn't in your, but you should put this in your notes. By the way, you guys are writing all your work in your notes, right? Because I'm going to grade your notes when we do this test. It goes 6 times higher. Okay, but they just want to know the difference. So the difference, we'll call this delta y of the moon. I hate when this does this. And we'll call this delta y of Earth. So we're going to say the Earth gets subtracted from the moon. So we'll say 51.7 meters minus 8.62 meters is about 43.1 meters. That can't be right. Let me do the math on this. So clear, 51.7 minus 43. Lost it. 43.1. Oh no, I did it backwards. It's 43.6. So 51.7 minus 8.62. 43.8. Yeah, I guess it does if you round it. That's the final answer. Any questions? All right. So let me post this real quick, and then we'll do problem number